podcast discussion. Simon Knowles, guest at the Robot Brains podcast by Peter Abil. This podcast is absolutely crucial. I cannot emphasize enough how important Peter's work is, at least from a podcast perspective. I don't know exactly what his scientific contributions are, but he's bringing in people like Andre Capati and now Simon Knowles. Simon Knowles is, I'm not sure exactly what his role is at Graphcore. I think he's a founder or co-founder. Graphcore is a chip company, a very interesting chip company, because they are one of those startups that started years ago focusing chip design for the modern version of AI, or in other words, for a linear algebra compute engine that is more specific to AI and less general, even like GPU. So I want to talk about it. It's very important. It absolutely affects our portfolio, and it affects pretty much anything we do. I think since we're invested in fundamentally new concepts and engineering practices with large impact, AI is a big part of that. And Simon's contribution in this field as an engineer, but also as a thinker and experienced practitioner, are just very valuable. That's why I want to share his insights in this episode. This is a Not Even Wrong podcast. It's May 28, 2021. This is Crindelco. For the day, we're up 50 basis points. The market's up 30 basis points. For the year, we are down 11.1%. The market's up 11.3%. We're underperforming by 22.4%. The market's still open. These numbers could change. So Simon has, again, I'm not sure if he was a founder, co-founder, but anyway, he had a big role in founding Graphcore. Graphcore is a UK-based chip company. They are making a very specific compute engine for AI. Now, what does that actually mean? So let me first lay out what they did different. In particular, the one thing that Simon continuously talks about is sparsity, which means that they have found a way to design a chip that can do massive amounts of calculations, but those calculations don't have to be very precise. Because the way we work in AI, in this probabilistic way that AI works, and maybe I want to just digress a little bit in explaining what a modern machine learning algorithm looks like, and then also what a corresponding semiconductor should look like in terms of supporting those algorithms. And this is kind of where Graphcore came from. This is what they thought about when they sat down to start the company. They were thinking, okay, we have ImageNet in 2012. ImageNet 2012 shows that with convolutional neural nets, you can recognize pictures and predict pictures, and then go from there and solve vision, solve language, solve a lot of AI problems that we weren't able to solve before. So what exactly is the underlying technology doing? The underlying technology is looking at patterns, is doing statistical analysis across large data sets to find particular patterns, particular predictive information that is hidden in the data, and then using sophisticated statistical analysis to then infer from the results and do the inference, which is basically make actions based on past data and past modeling results, make actions for the future. In order to do that, you have to do, in particular, very massive calculations. So, for example, you have to find a simple thing to do is you have to fit a curve. So you have a lot of data, and then you have to fit a certain curve or find a function that corresponds to the data. So then when you have a new data point, you can predict roughly where the corresponding result should be. So let's say a very simple two-dimensional problem where you have x, y, and you want to find the relationship between x and y. You have a lot of data, you don't know the function, but because you have a lot of data, you can then extrapolate the function from the data. So let's assume you find out that the data is a linear function, so every x maps to y by the factor of 2. So the function would be y equals 2x. And now you have found that, and now if you get a new x, you know that the y, the corresponding y, should be just 2x. So this is roughly what AI is doing at a much more of course, complex scale and much more, of course, multidimensional, etc. But the point here is that Graphcore is saying, and Simon is saying, that you don't have to be very precise here. You don't have to have, let's say, 16 digits after the comma precision, floating point precision to the point where you have to be incredibly precise. You have to be very precise in a lot of engineering practices. For example, when SpaceX is shooting rockets to space and in the future to Mars, you will have to be very precise. But in terms of AI, the way AI works, you don't have to be precise. So you can start using sparse computing, which is one of the things that Graphcore is trying to do and is very good at. So this is part of the reason why Graphcore thinks they have value added in the sort of chip design world, because the other companies, in particular Intel and NVIDIA, that are very big in sort of designing and selling general purpose semiconductors to the world, they have to have both, because they're general purpose, they sometimes have to match very precise job descriptions for engineers, but they also have a lot of room for sparsity. So they kind of have to straddle those two worlds. Graphcore is saying we're not going to sell semiconductors for high precision engineering practices. We're just going to do it for AI. And I think this concept of sparsity kind of made me think it's a very important question, because in the podcast with Peter, Simon talks about the concept of the human brain and how the human brain has enormous amounts of information but doesn't have a lot of power budget. We have a very low power budget and very high ability to process information. And this is something that we humans are still not able to produce artificially. We don't know how to do it. Now I want to bring in my latest read, which is The Science of Can and Can't by Chiara Marletto, co-worker with David Deutsch. And I think the solution to the future of AI, which is high processing, high compute, and and low power budget, is going to be in the counterfactual discussion. Before I go there, I just want to mention the second big sort of innovation that Graphcore is doing. And what Graphcore is also saying is that you want to keep the memory very close to the compute. Why is that? Because part of the problem of any large compute engine is the memory. The memory budget is becoming much more of a problem. And that has two implications. One is space. So you need space on a chip for memory. But the more important problem is you need to bring data in and out all the time. And that is the problem with power. So moving data in and out. And a typical algorithm, a typical machine learning algorithm actually exactly does that. It continuously adds data and then moves data forward in the neural net and then backwards. So there's forward propagation, backward propagation. There's all these moves back and forth. And that is sort of the fundamental problem that Graphcore is also solving, which is, okay, if you have to move data a lot, back and forth a lot, then you need to have a way to make it energy efficient. And one of those ways would be proximity to the compute. So that's the two big vectors that Graphcore is attacking. One is sparsity. The other is not having a whole lot of movement in and out of the from compute to memory and back and forth. So these are the two big things that Graphcore is attacking. And I think I want to mention this whole memory conversation and tie it to the counterfactual conversation, because I think the fundamental problem, and this is, here's my thoughts. I think that we have an ability to build very large compute engines. What we don't understand is how to coordinate and communicate the results in an intelligent way so we don't have a large power budget. I think this is the fundamental problem that we face with the next level of AI, or that we're going to face. We're already facing it, but we're going to face it. I want to add another quote from Vijay Pandey, which stuck in my mind a few days ago in one of his interviews that he gave about the protein folding at home project that he started 20 years ago when he was at Stanford. He said that there's one thing to do parallelism at scale. there's one thing, which is you can do a task alone, or you can have a lot of people do the same task and then reduce the time that it takes to finish the task. But he said, if you took a class of 60 people and you gave them all a test to solve, and you told them now, listen, you all 60 people can work together. However, now instead of 60 minutes, you only get 1 minute. You see, that math doesn't work. The 60 people could each one work alone, solve the test in 1 hour, more or less. You get, A's, B's, D's and stuff, but they could all do it roughly. But if you now told the 60 people that they can all cooperate, but they only have 1 minute, so you're taking the number of entities that do compute from n to 60, but you're reducing the time from 60 to 1, from 1 to 60, and so the number of entities goes from 1 to 60, and the time goes from 60 to 1. Well, that doesn't work. And the reason it doesn't work is because of coordination and communication. We just wouldn't be able to communicate fast enough and coordinate. You do this, you do that. Hey, what's your result? If we had some time, if we could organize, and this is exactly what an algorithm does, this is what computer science does, organize these things, or at least parallelism, as in particular, Berkeley is very big on that, like things like Spark and all these things in particular are actually, if we talk about distributed computing, if we talk about any kind of problem in distributed computing, it's always about coordination. Okay, how can we all do this task together faster? And then how can we coordinate? This is what a company is about. This is, Kenneth Arrow, the theory of the firm back in the 1930s. He said, why do we need a firm? Well, we need a firm because we have a lot of transaction costs, coordination costs. We have to do a task together. Let's say 50 engineers have to build the Golden Gate Bridge. It has to be done within the context of a firm, because to coordinate, we could use 100,000 people to build the Golden Gate Bridge, but how do we coordinate? How do we communicate? It is way too expensive, way too difficult. Today we can do this a little bit better, but we still need firms, we still need companies, etc. Now, let me get back to the conversation with Simon Knowles. So what he's saying is that the problem with artificial intelligence today is that we can put a lot of compute on a chip. We can even put the memory on a chip, but the whole coordination problem, that's the issue. And this is where the power budget is the key. And now I want to bring in Chiara's counterfactual conversation, because here's what I'm kind of getting from the book. I'm just in chapter 2, but I'm getting from the book that information as defined in Chiara Marletto's book, information is defined as something which could be either this or that. This is information. So typical information would be a transistor. It can be either 0 or 1, plus or negative. That's information. Information has this property of having a counterfactual. It could be this or that. It is there, and it could be this or that based on certain conditions. This is information. Now, the human brain has a lot of these counterfactuals. The more counterfactuals you have, the more information you have, or the more information you can store. The problem is, the optimization problem is, how do we coordinate those counterfactuals in an intelligent way so we don't have a large power budget? This is what nature solved with the human brain, because we have a very low power budget. And I think it's because we found ways to deal with these counterfactuals. And I don't know, I have to do a lot more research and thinking about that. But I think to try to tackle the problem of artificial intelligence, large compute, large memory, and low power budget, this trifecta can be solved by attacking this problem from a counterfactual perspective and finding ways to coordinate in a more intelligent way. Like Vijay Pandey said, the problem that the floating folding project was solving wasn't really the parallelism, it was the coordination. How do you solve a problem in parallel at scale? By coordinating in an efficient way so you don't waste energy and resources. This is, I think, not just the protein folding problem, but it's the problem of intelligence in general. And this is the big insight I got from this week, from reading Chiara's book, from listening to Pandey's comments about the protein folding project, and now from reading this interview with Simon Knowles and Peter Abil. I think, or listening to it, this is the fundamental problem. So we have a lot of, the more counterfactuals we have, the more information, the more potential. But how do we reduce the power budget to the point where we can do this efficiently? And this is a question of coordination. Now, to finish this episode, I want to now draw the arc to our portfolio. Tesla is also in the business of producing semiconductors, in particular an inference engine for vision. And I would be very happy to talk to them about this particular problem, the same problem, sparsity and memory and coordination of memory. So how do you bring information in and out? Now, Tesla, I think, already has a very, very strong constraint on power because the inference engine has to be in the car and they cannot use electricity or they have to reduce the power budget. So this is already part of the problem. And I think that's why I'm so bullish on the Tesla solution, not just from an algorithmic perspective, what Andrej Karpathy and his team are doing, but also from a semiconductor perspective, because they already have the big constraint. They have a much bigger constraint than anybody else has, which is power budget. And this is unbelievably bullish on the Tesla. What I'm trying to say here is that the constraints that Tesla has put on itself, just by nature of who they are, they're making an intelligent electric robot that has to drive on its own. They cannot waste power, so they have the constraint of power budget. They have the constraint of sensors we spoke about in one of the past episodes, that they got rid of radar. Now they only have vision, and part of that is because of the cost, but also they need to find solutions that can work just with vision. It's enough, but it's much better to constrain yourself than to use all these other sensors and then pretend that maybe one day the cost will come down. It's not just about the cost, it's also the power budget and the complexity of the algorithms, which have to be reduced, which have to be sort of on an Akram's razor type way, have to reduce to the simplest form possible, or another word that is used in science is parsimony. So instead of having this complex solution to solve the problem, how do I turn left? You have the simplest possible, or the lowest common denominator, or I don't know, whatever you want to use, this lowest possible solution that still makes it work. So I think Tesla is on a very good path. I think Simon's comments are complementary to what Tesla is doing. I think Graphcore is not competing with Tesla, in case anybody thinks, because Graphcore is attacking very different problems. I think Graphcore lives a lot more sort of in the cloud data center space right now. They might get into the Tesla business at some point, and I wouldn't be shocked if maybe even there could be a cooperation or an M&A transaction at some point. It's not impossible to think. I wouldn't be surprised if somebody gobbled them up, and maybe even Tesla. I don't know how far Tesla's AI, semiconductor AI efforts are at this point. Last time on the call, Musk actually said that even what they have now, they're not even to fill the tank right now, so they have a lot more capacity on the semiconductor front than they're actually using. So they're way ahead of their own metrics. But again, I think to summarize this whole situation, to me looks the following: we need to solve sparsity, we need to solve memory in-out issues, and we can only solve that by finding the best way to coordinate all of that, the same way the human brain has done it over millennia. We of course we have the advantage of design, and we don't need to use natural selection, so we can do it faster, and we will get there. We will solve this problem of finding the trifecta of large compute, large memory, and low power budget by finding better ways to coordinate. Thank you.